water, a prime necessity of life, draws little attention until the lack of it threatens man's existence. Confident that an endless supply exists in lakes, rivers, and streams, man has polluted and wasted water in many parts of the world. Elsewhere, because his land has become parched, scorched, and withered by drought, man has packed up his belongings and migrated thousands of miles to relieve his thirst. In ancient times, as well as today, man has fought over this life-sustaining gift of nature. For without water, man is nothing, and there is nothing to sustain life. Man's present concern about water results from a developing worldwide shortage of usable water of plenty. Although water covers 75% of the Earth's surface, it isn't always found where it is needed, when it is needed, and in sufficient amounts and purity. Of all the water on Earth, more than 97% is in the ocean, not fit to drink, and too salty for irrigation. 2% of the Earth's water is frozen and useless in glaciers and ice caps. The remaining 1% is usable, but not utilized properly or distributed evenly. Within 20 years, the world's demand for water will double. Americans, who now use more than 350 billion gallons each day, will require 600 billion gallons daily in 15 to 20 years, and 1 trillion gallons or more by the end of this century. What is the solution to the water shortage problem which plagues the world? There is no single answer, but several steps can be taken to reduce the shortage. These include more efficient use of water in agriculture, better water storage and distribution systems, and the control of water pollution and wastage. In many areas, the most economical step lies in desalting the seas. Desalting is one of the oldest methods of obtaining fresh water. It was used on a small scale even in ancient Greece. The emphasis today, however, is on desalting large amounts of seawater at the lowest cost possible. There are several ways to separate the water and salt in seawater. This may be done by freezing it, which is also known as the crystallization process, by squeezing it through special membranes, and by boiling it, better known as the distillation process. The principal impurity of seawater is common salt, sodium chloride. In each salt crystal, there are equal parts of sodium ions and chloride ions. As the salt is dissolved in water, the ions are freed to migrate among the water molecules. Each ion carries an electric charge, which attracts a layer of water molecules. The water surrounds the ion like a cover, and both move about together. The problem in desalting is to separate the water from the salt. In the crystallization process, part of the seawater is frozen when it is cooled by evaporation under vacuum. The water molecules in freezing form into ice crystals, while the salt remains in the liquid. The ice crystals are then removed, rinsed, and melted to make fresh water. In the squeezing or membrane process, some types of membranes permit water to pass through them more easily than the salt. This is known as the reverse osmosis method. The electrodialysis method uses two membranes to separate the salt and water. Positive and negative electrodes are also utilized. When an electric current is applied, the negative ions pass through one of the membranes, while the positive ions travel through the other, thereby leaving the fresh water behind. In the distillation process, the seawater is boiled. The water molecules turn into steam, which is then condensed to form pure water. The salt is left behind. This distillation process appears to be the cheapest at present for large-scale applications. The problem with desalting plants is not in making them work, but in building them at low cost and in reducing their cost of operation. Extensive research is being conducted in the United States and abroad to find ways of reducing the cost of desalting seawater. Included are studies of desalting facilities powered by nuclear energy, since this form of energy may be the cheapest, especially for large-scale applications. The U.S. Atomic Energy Commission and the Department of Interior, jointly, are conducting research on the use of large-scale nuclear desalting plants. Such large plants would not only desalt seawater, but could also provide simultaneously low-cost electrical power for homes and industry. At AEC's Oak Ridge National Laboratory, various concepts of reactor-powered desalting systems are being explored, including research on the development of huge evaporators. These programs are aimed at reducing the cost of desalting large quantities of water. One of the major cost factors involves the evaporator, the equipment in which salt water is converted into steam. With a single evaporator, the heat used to make the steam is utilized only once. Actually, evaporators are built in series so that the initial input of heat can be reused many times, and each time additional quantities of water are distilled. For instance, energy from a boiler or a reactor is used to heat seawater, which boils in the first vessel to produce steam. This steam is pure water vapor. When it is cooled slightly, it condenses to form distilled water. In doing so, it releases almost its original amount of heat. This heat then can be used to produce steam in the second vessel or stage of the evaporator system. The sequence can be repeated many times, each time at a slightly lower temperature and pressure until the temperature of the steam is too low for further use. From an economic standpoint, this is the result. With a one-stage evaporator, the heat cost is high and the cost of equipment is low. With two stages of evaporators, the heat cost drops to nearly one-half, although the equipment costs more. Additional stages will raise the equipment cost, but also reduce the heat cost progressively. As a result, the designer seeks to balance heat and equipment costs so that water can be produced at minimum cost. Thus, the designer must consider the cost of each stage of evaporation and the cost of the heat initially supplied to the evaporator to achieve the most favorable plant design. One method of reducing the cost of an evaporator stage is to use more advanced heat transfer techniques, thereby reducing the size and cost of the equipment. Another cost-cutting approach involves the use of very large units, since many economies are possible in large-scale construction. Still, another way to reduce costs is to use dual-purpose nuclear plants. In such plants, the reactor would generate steam, which would then operate the turbogenerators to produce electricity and subsequently provide the energy for the desalting plant. With this concept, the production of electric power, along with the desalting of seawater, offers cost advantages to both products. The use of large-scale dual-purpose plants calls for a major scale-up of the reactor heat source. Such reactors may be many times larger than those in use today. The scale-up of reactors and other components, as well as finding improved methods of construction and operation, are the principal technical problems. And only through the construction and operation of larger plants can needed operating and economic data be obtained. Studies show that several advantages may be realized by using large reactors in dual-purpose plants. For instance, reduced electrical costs would benefit industrial, commercial, and residential consumers. Another attractive feature is that nuclear plant economics do not vary greatly because of geographic location. This would be a boon to those areas where industrial development has been retarded because they are not convenient to conventional fuel sources. Because of its compact nature, nuclear energy is ideally suited to situations where logistics are difficult, since nuclear plants do not require extensive fuel storage or transportation facilities like conventional power plants. The smoke and smog problem, too, is practically eliminated with nuclear energy facilities. Nuclear fuel costs are expected to decrease as fuel technology is improved and a larger fueling industry is established, and as more advanced reactor concepts are developed. The rapidly rising rate of the world's population is not only increasing the demand for water, but is also creating famine conditions in various parts of the earth. Current food shortages point to the spread of famine. By 1980, it is predicted that unless something is done to increase food supplies, famine will spread throughout portions of Asia, Africa, and South America. Additional water may be a key solution to this problem. Most people are not aware of the large amounts of water required for growing their food supplies. Although 100 or more gallons daily per person is common for domestic and industrial needs in the United States, another 4,000 gallons daily for each person is consumed in growing his food supply. A minimum diet requires at least 2,000 gallons daily for growing food with present agricultural methods. The development of large nuclear desalting plants, which could supply fresh water for household and industrial uses as well as for agriculture, may be mandatory to eliminate famine. To meet this threat, many nations, including the United States, have announced desalting as a national goal. Of the total land area in the world today, only about 11% is now being used in raising the world's food supply. There is much arid, dry, but fertile land lying idle throughout the world, several times the total area now being used for growing food. Nuclear desalting may make it possible for man to settle in new areas where he can live and raise his own food. Many desalting facilities are in use today, and large nuclear desalting plants are being studied or planned for California, Mexico, Israel, and the Soviet Union. The President of the United States has promised full cooperation with other nations in developing desalting technology. In a recent message, he said, "The time is coming when a single desalting plant, powered by nuclear energy, will produce hundreds of millions of gallons of fresh water and large amounts of electricity every day. Such a plant can foreseeably provide water to industries and thirsty cities at prices they can afford, and may eventually benefit agriculture as well. Our government is proceeding with an aggressive program of nuclear desalting. We invite all countries to join with us in this effort. What we learn from this program will be shared with the world." Already, a major water supply agency and 3 utilities are moving toward joint construction of a large dual-purpose nuclear-powered desalting project in Southern California. The government is participating in the development of technology for this project, which is expected to be in operation in the early 1970s. It will supply 150 million gallons of water daily and have a gross output of 1,800 megawatts. Thus, the coupling of two emerging technologies, nuclear energy and desalting, can provide immeasurable benefits in the years ahead. This is one of today's most challenging areas of research and development, and one which holds great promise for answering the needs of future generations. Through the peaceful use of nuclear energy in desalting the seas, human suffering may be alleviated throughout the world.